you apply such a rule as defined before by finding an embedding into the graph, and then why does it not? Okay, now it rewrites. And then you basically execute this step. Now you have another graph. You can play the game again, find another embedding, and so on, and so on, and so on. Do this a finite number of times. And this produces you what's called a derivation trace. So a sequence of steps where the data is the rules applied, in this case all the same, and then each time you need an embedding. That's called a derivation trace. But you could think, I mean, this community will immediately think about these pictures with these wire diagrams. I mean, think string diagrams, but it's not string diagrams. And you could think that maybe there's some interesting data contained in these overlaps already before you compute the action. Yes? And so the philosophy of these pathways is very closely related in that you try to reason about the upstairs part of this diagram, the green stuff, rather than any concrete state, because that will be the thing you can abstract and do causal analysis on. And slight complication is that most of the interesting data types, like biomolecules, you need sort of to constrain the data type a bit. There's a way to do this in this formalism, indicated through these little triangles here. And for example, here you cannot have these sort of outwards pointing edges. That step would produce something like this, so it's not executable. And so this, for example, is permissible and so on. And you can produce some possible sequence of step. This is now quite a bit more complicated, but it's still within the exact same formalism and can be done. I recently developed the technology to do this with Jean Crévin at IRIF in Paris. Okay, and this is perfect. I have 2 minutes to present the main results. Okay, so the idea is you have such a derivation trace. That's a classical object. And now contained in it is some data. And the data, I will show a way of extracting from this derivation trace what I call a tracelet. So the idea is there is this upstairs part, which is somehow the minimal causal account of what is actually the relationship between these steps. And then one piece of data says how this overall construct applies to the initial bit. That's essentially the concrete mathematical equivalent of this little picture I showed before. Okay, and then I will say that actually this construction achieves something which hasn't been possible before, namely to statically generate these pathways. It's something which cannot be done. So far, pathways were extracted from data. This allows to generate them. Okay. Good. So the main engine behind this is a property which I call associativity. I mean, it's something if you perform. So these is a composition of 2 steps, which makes the back face of this diagram. And then you compose with a 3rd step. And there's a way to produce this shape. And now, so interestingly, from order of associativity. So essentially, you are sort of bracketing which way these things overlap in 2 possible ways. And that's what I call associativity property. And it works for, if you carefully choose a category, you have to, there's some work to be done, but this works for exactly those types of rewriting theories which are used in biochemistry. And now there's some complicated proofs, but okay. And then the point is that the commutativity of this tube means that if you take the diagonal, basically this sequence of spans is uniquely coded in both possible ways. And this means that if you take the diagonal, there's suddenly something which looks exactly like this data type of derivation traces I showed you before. And so this is what I call a tracelet of length 3 in this case. So associativity means that there is a way to compute uniquely these minimal causal accounts of rewriting. And now, sorry, I'm going to skip the picture because, okay. Sorry. Okay, and so the key point is that now you have a choice of whichever way you please to recursively produce yourself with these minimal accounts by simply some type of composition operation. So each individual rule gives you a tracer of length 1, just copy the rule. But then if you have a tracer of length n, so this is a recursive data type, you can take a tracer of length 1, choose an overlap, push out, and do this rewriting step here. And if you have conditions, that also works. Okay, and you produce yourself a longer tracelet. And the interesting bit is that data type non-destructively encodes also what is the overall composite application of rules. And okay, basically this foot of the diagram always codes if you span compose, what's the net effect of this rule. And so these things are compositional. So this composition can be lifted to all the ensemble of all tracelets in precisely the same idea. Sorry. and it has some nice associativity properties and so on, but I'm running short on time. So essentially what you get is exactly what I advertised. So every concrete derivation trace is uniquely coded as the application of its underlying minimal causal account, its tracelet of length n, and this way it applies to the state. And now comes the main point. This is compositional and on top decompositional. So you can effectively, if you have such a tracelet, it's a sequence of events, and you call these little blocks like the subtracelets, then you can choose any consecutive block and perform something which is called, analysis step of concurrency, but okay. And so you can, by using this characterization step, you can say there's a minimal account for this particular subsequence plus how it embeds into the bigger one. If you do this a number of times, you can now reason about arbitrary causal interactions within a certain sequence of events. And this is the key point. So now you can use classical concurrency theory to define equivalence. So it's a notion from classical concurrency theory how two steps might be independent of one another, meaning they can be pushed in different directions. And if you use this concept, you end up exactly at what should be the notion of a pathway. So, sorry, I'm going to take 2 moments. It's just 2 moments. So, of course. So a pathway in biology says you want to find one final event, which is like find me this molecule, or and you want to say only give me the past of this event. Without any side reactions. You only want those that cannot be commuted away, so to speak, or are independent of this process. And so finding pathways means finding sort of a high-level explanation in this insanely complicated writing system simply by giving these minimal causal accounts up to this equivalence. And if you do this, you can give an algorithm which generates statically the ensemble of all of these pathways. So it's an exhaustive enumeration procedure if you want. And just to conclude, so here's a little example. You have a rule that takes an edge and then tries to remove one vertex and then recreate it. You can only remove it if that vertex was not having any other edge other than this one incident. And then you ask what are the minimal causal accounts of finding an edge that has been necessarily dependent on the previous n-1 steps. And you find out from this algorithm that the only things that can happen are that these are these staircase type diagrams. And that comes directly from the mathematics. There's no interpretation. Afterwards, you can see why this is the case. But this is a type of high-level explanations and combinatorial properties you can extract with this algorithm. And yes, and with that, I would like to conclude and maybe also ask if there's ideas in this audience, maybe what. Thank you.